Okay, welcome to 6-7, Investigating Graphs of Polynomial Functions. In this one we want to use properties of end behavior to analyze, describe, and graph polynomial functions, and we want to identify and use maxima and minima to solve problems. A lot of this will be done through the calculator, and if you can use your notes that will help, or for a note card for the end behavior. Understanding that end behavior is going to be critical in this one. So on page 453 you have the different types of graphs of polynomial functions that we've seen and possible ways that they can look. So notice how a quadratic function degree of 2 and a quartic function degree of 4 both can have graphs that go in the same direction. Linear and cubic and quintic functions have graphs that end up going in opposite directions. And that creates what we call end behavior. End behavior basically says as it approaches positive infinity, which way is the graph going? As it approaches negative infinity, which way is the graph going? In other words, as it goes to the right, which way is it going, up or down? As it goes to the left, which way is it going, up or down? Okay, so basically, again, with end behavior, you want to make sure that you understand which way it's going, but you need to, here's a graph or chart that's going to show us something. If the leading coefficient, remember it's always based on the leading coefficient. Leading coefficient is a number greater than 0, positive number. Then for odd degree and even degree polynomials, we can separate it like this. Odd degree polynomials would go in different directions. So that means this, and then even degree polynomials. Okay, so I'm giving you graphs of each one, and then you can see here, and I'll explain. Okay, on the odd degree, if the leading coefficient is positive, as the x goes to positive infinity, in other words, as it goes to the right, notice that the graph is going up. So the polynomial function will say p of x goes to positive infinity also. And this is how you're going to have to word this in the test and on the quiz. So you've got to be prepared for this. If, as it goes to the left, in other words, it's going to the left, because notice how I'm saying this, going to negative infinities to the left, that the graph is going down. So we would say that as p of x is approaching negative infinity. Because you never really reach infinity, you just get close. For the evens, as x approaches negative infinity, as it goes to the left, p of x goes to positive infinity because it's going up. As it goes to the right, the graph goes to the right, x goes to positive infinity, the graph goes to positive infinity. Okay, so you gotta make sure you see it like that. When it's a negative, when the leading coefficient is negative, as x approaches negative infinity, goes to the left, p of x goes to positive infinity. It's going up. As x goes to positive infinity, p of x goes to negative infinity. And continue the same thing. On the evens, here you can see how it goes. And notice that we're saying that they're both going to negative infinity, which means they're going down. So keep in mind how this reads. And like this is true for all of them. So I don't care if it's an odd degree, that means like a degree of 1, 3, 5, 7, 9. This is what would happen. Evens, 2, 4, 6, 8, that type of thing. Notice that odds always go in opposite directions, evens always go in the same direction. Okay, so for example, we look at this function, negative 4x cubed minus 3x squared plus 5x plus 6. Okay, leading coefficient is negative 4, the degree is 3, so the leading coefficient has a negative, The degree is odd, so that tells me something about the end behavior. I don't even need to see the graph, but based on my notes, I could tell something about the end behavior. As x approaches infinity, and negative infinity and x approaches infinity, I should be able to tell, just by looking at, say, the notes or my formulas, that p of x is going to be going towards, at negative infinity, it would be going towards positive infinity, and at infinity it's going towards negative infinity. And here's a graph to kind of demonstrate that. Negative infinity, again, is on your left, positive infinity on your right. And you can see the graph is going down as it heads to the right. It's going up as it heads to the left. So that's saying as x goes to the left, it's going to positive infinity. As it goes to the right, it's going down towards negative infinity. So you can kind of see how this works. Yes, you can use a calculator to kind of see that, but at the same time I'm trying to get y'all to understand these graphs a little bit better so you can see that without necessarily having to do it on a calculator. Okay, so another example here. X to the 6 minus 7x to the 5th plus x cubed minus 2. Leading coefficient is 1, which is a positive. Degree is 6, which is an even. So that tells you the end behavior both as x goes to negative infinity and positive infinity, the polynomial function should be going to positive infinity. Without having to necessarily look at the graph, but I believe I even show you the graph so you can kind of see that. And you can see both endpoints are going towards positive infinity. Okay, so now using graphs to analyze. Okay, and here's just some examples. Can you tell me what type of degree you have here based on like the look, and is it the leading coefficient positive or negative? Now on the first graph you can see here that they're going in opposite directions, so that should tell you that it's an odd degree. Then the other one, they're going in, and the leading coefficient here, since negative to negative, positive to positive, the leading coefficient should be positive. Here they're both going in the same direction on the second graph, so that's an even degree. And then from there, since they're both going down towards negative infinity, that would tell you it has a negative leading coefficient. And that's pretty much it for the analyzing. Here's some steps for graphing polynomial functions on page 454. You need to make sure you plot your real zeros and your y-intercept. You need to make some points, plot some points. This is all kind of nice. This is what I would say. What you need here is this. You need to get your zeros, your y-intercept, know your end behavior, and preferably find the local max and mins. And you can do this with the calculator. So a lot of this still, I would say, you could do with the calculator. Okay, so we're going to graph this function. I only got a couple more here. X cubed plus 3x squared minus 6x plus minus 8. Okay, y-intercept is negative 8. That's automatic because it's the last number. The last number, the number that's all there by itself, that's your y-intercept. Okay, zeros. This is to help you identify the graph on your own. Okay, you could just graph this on the calculator, write down the zeros. You could do synthetic division because your factors would be 1, 2, 4, and 8. And we'd find these three zeros. Remember, there's 3 possible zeros here, answers. And then you would have like these points. So there's negative 8, there's negative 1, there's 2, there's negative 4. Okay. Now, based on the end behavior, see, at this point you would need to know the end behavior. As x goes to the left, the polynomial function should be going down. Okay, as x goes to the far right, so at the 2, the polynomial function should be going up. Okay, then that point should be heading towards y-intercept and then curve back up and turn. The only thing we need to find now is those max and min points, those turning points. Those turning points are just what we call maxima and minima. And those we can find, we've done it before. You've done those maximums and minimums just by doing a graph trace. Okay, so that's what we're going to do. We're going to use the end behavior, or we're going to also use the turning points, all that, to find the different points using the calculator. That would enable you to graph it on the test, or at least even choose the right graph based on that, or answer any type of multiple choice question, whatever may come through my mind. Now, what you need to remember here is local maximums. There's different types of maximum minimums. Local maximums are when the high turning points, the high points. Every time it turns, like it's going up and then turns to go back down, that's a maximum. Local minimums are low turning points. Every time it turns like it's going down but then turns around and goes back up, that's a local minimum. There can be more than one max and one min. That's why we're calling them local. Okay. Absolute max, absolute mins, those are the highest and lowest points. So let's say you see two maximum points. Okay, the highest one, both of them would be local maximums. The highest one would be considered the absolute maximum. Okay, so for example, let me draw this in here. If I saw something like this, okay, you can see here, there's like two maximum points. Those are, both of them would be local max. But then this one right here would be considered the absolute max. Now there's only one min point. So that min point is not only a local min, it's also the absolute min. So keep that in mind, that it's possible to have more than one max point. Okay, so for example, and this one I would recommend doing through a graph. We're going to have x cubed minus 2x minus 3. Use the calculator. I already did this. I already used the calculator in the graph trace function. I graphed it there to find your different points. So we want to find the max and the min. And according to this, the local max here was negative 0.82, comma, negative 1.91. The local max, or local min, was 0.82, negative 4.09. Since there is only one of each, those local max and mins are also the absolute max and mins. So keep that in mind, and that's pretty much it. Now we can use that to help solve, and I'll discuss that more later. Help solve functions, or help solve like specific types of problems, and we'll discuss that a little bit more later. Otherwise, that is it for 6.7. It shouldn't be that difficult, and if you do have any questions, feel free to ask. Thank you very much.